hello everyone, and welcome to the Frontiers of Parameterized Complexity seminar. Our speaker of the day is Bart Jansen, who will speak on algebraic sparsification of decision and maximization constraint satisfaction problems. Please, Bart, the floor is yours.
Thank you, Fedor. Thanks for the invitation. It's nice to be at least virtually in Bergen, if not physically in Bergen. This is joint work with Hubi Chen, Astrid Pieterse, and Michał Włodarczyk, several works. And let me say beforehand that if you have any questions, don't hesitate to put them into chat. I have my eyes on one part of the screen, which also has the chat in it, so don't hesitate to ask if anything's unclear. What I want to take you through is the landscape of sparsification for constraint satisfaction problems that we've been discovering over the last years. And we'll start our discovery down in the shallows where things are nice and easy, and we will gradually climb our way into more generality, passing a number of different concepts along the way. After we explore the mainland, which is where decision CSPs live, we will also head on over to the more relatively recently discovered island of maximization versions of CSP and what we know about compressing and sparsifying them. Good. Let's start with a general introduction to the type of problems we'll be considering. They are very much related to the tools of parameterized complexity, but in a slightly different setting. Constraint satisfaction problems are a general class of decision problems of the form find an assignment to a sequence of variables that satisfies all constraints. There's various things of what can be meant by a constraint. Some classic examples include a constraint on three variables x, y, and z, which in the 3CNF problem is satisfied if at least one of x, y, and z is true. You can have the not all equal variant of the problem, where a constraint is satisfied if at least one literal evaluates to true and one evaluates to false. And there's, for example, the 1 in 3 set problem, where a constraint demands that exactly one of the variables x, y, z is true. The complexity of the constraint satisfaction problem crucially depends on what type of constraints you're allowed to write down. And we'll make this more formal as we go along. What is the goal for today? It's to achieve polynomial-time sparsification algorithms, to give an algorithm that efficiently reduces any n variable instance to an equivalent one on order of n to the d many constraints, for d as small as possible. So typically we look at NP-hard problems. We don't expect to solve them in polynomial time, but we aim to at least give some provable sparsification guarantee on how to deal with these NP-hard inputs. Since we're starting out our journey in the shallows, let's start with a very down-to-earth concrete example to warm up for the type of ideas we're going to be applying. So the idea is that a constraint in a problem is redundant when it's implied by others. So consider the following instance on 5 variables a, b, c, and d of the 1 in 3 set problem, where again, a constraint is satisfied if exactly one of the 3 literals satisfies to true. Let's rewrite these constraints in an algebraic form. Using the convention that true is 1 and false is 0, we can say that the 1 in 3 constraint on a, b, c is satisfied exactly when a plus b plus c is equal to 1. Similarly, we can rewrite constraints with a negation by including 1 minus the variable's value. And if we rewrite all constraints in the form of an equality over these variables, we can then see that the fourth constraint we have can actually be written as the first constraint plus the third minus the second. For example, we have a single a, these two b's cancel, we have c minus c plus c, we still have a d left over, these cancel, and we have an e. So whenever the first 3 constraints are satisfied, the corresponding equalities hold. When some equalities hold, then any linear combination of them holds as well, which means that the 4th constraint was also satisfied. So we see that in this situation, removing the 4th constraint will exactly preserve which assignments satisfy these constraints and which don't, and therefore this constraint is provably redundant. This leads us to the following general principle. Suppose that we can represent each constraint by an equality And we find that the equality of a certain constraint C can be expressed as a linear combination of the equalities of the remaining constraints. Then this constraint is provably redundant and can be omitted from your problem. All right, this is the principle that we're going to work off of. And let's see how we can apply this systematically for the 1 in 3 set problem and what we can then guarantee about the number of constraints we end up with after sparsification. So here is the sparsification routine. As input, it gets an input of 1 in 3 set on n variables with some m constraints. We write each constraint as a linear equality using the 1 minus trick to deal with negations. And then we rewrite these equalities in matrix form and move over the constant from the right to the left side, so we have 0 as right-hand sides. So what we then get is a system of equations that we can write in matrix form with zeros as the right-hand side. We have one row for every constraint that was in our input. We have one column for every variable that was in our input, and we have one additional column for the constant term in these equations, right? And then we know that an assignment to the variables satisfies all constraints precisely when the corresponding system of equations is satisfied. How can we use this to do sparsification? Well, if we have a matrix, we can compute a row basis of this matrix, for example, by Gaussian elimination. We know that the size of a row basis is the same as the rank of the matrix, which is at most the number of columns. So with Gaussian elimination, we can compute a basis of at most n plus 1 rows, with the guarantee that any constraint, row, equality, these are all equivalent in this setting, that wasn't in the basis can be expressed as a linear combination of those which are in the basis. And by the redundancy principle, we can safely forget them from our input without changing the set of satisfying assignments. So what we can then do is output the instance on the constraints corresponding to those rows in the basis. This gives us that for all positive integers d, there's a polynomial-time algorithm, which you can feed an instance of the 1 in d set problem. It outputs you a subset of at most n plus 1 constraints, such that a truth assignment satisfies the original constraint if and only if it satisfies the subset. So this is a prime example of sparsification, and it's very strong sparsification because the number of constraints we end up with is only linear in the number of variables. Good. Before we head over to more intricate types of constraints and their sparsification, let me make a brief note on the number of constraints versus the encoding size that you need in such a system. We saw that this 1 in d set problem could be sparsified to at most n plus 1 constraints. Well, if you encode the resulting input as a binary string, how much bits do we need? If we treat d to be a constant, then each variable or its negation can be indexed in log n bits. So then you need d log n bits to write down one constraint. So the overall input with n plus 1 constraints remaining can be encoded in the order of n log n bits. All throughout this talk, we're going to focus on CSPs that have constant arity, so that the maximum number of variables to which a constraint is applied is a constant. And therefore, you can think of the encoding size as being roughly equivalent to the number of constraints we end up with up to a log n factor. All right, so with this rough correspondence in mind, let's think about how optimal our sparsification is and what optimal sparsification could look like for other types of CSPs. For the 1 in d set problem, we sparsify to n plus 1 constraints, and this is asymptotically optimal. If you could reduce to little o of n constraints, then there would basically be at least one variable that's not in any constraint anymore. Then by repeating your sparsification, you get rid of another variable, and after a polynomial number of rounds, you would have a constant size instance that you could solve by brute force, therefore showing p is equal to np. So for 1 in d set, this strategy is asymptotically optimal. What can we say about, say, the standard DCNF set problem? Well, it's easy to sparsify it to on the order of n to the d constraints simply by eliminating duplicates. If you have n variables, there's 2n different little goals you could write. So 2n to the power d different choices of what goes into a clause. So order n to the d distinct clauses. So if you just throw out duplicates, This is the number of constraints you end up with, and unfortunately, that's the best we can do. There's a very nice proof by Del and Van Melkerbeek that for all positive d at least 3, you cannot have a polynomial time compression of instances of d, c, and f set on n variables into equivalent inputs on order n to the d minus epsilon bits for any positive epsilon, assuming that NP is not in Cohen P/poly, which is a well-established conjecture based on which to prove complexity lower bounds. So the lower bound rules out more than you cannot find a subset of the clause that preserves your answer. The lower bound even says if you get to rewrite your input as an input to a different decision problem, but it needs to have the same yes/no answer and have this upper bound on the number of bits, then already that is provably impossible. So this is a very strong lower bound. All right, let's survey what we know so far. For 1 in 3 set, we can get a linear number of constraints, and 1 in 3 clauses being satisfied correspond to the number of satisfied literals in every clause being 1. For 3 set, we got a cubic sparsification, which was the best possible, and a 3 clause is equivalent to saying the number of satisfied literals is either 1, 2, or 3. Now let's look at something in between. A not all equal clause is satisfied, well, when the number of satisfied literals is larger than 0, but smaller than the total size of the clause. And we will see that the freedom in the number of different ways to satisfy a clause will determine what the best sparsification size is we can get for such problems. Let me make this concrete. If we have a not all equal clause on the literals, which is good if they are not all false and not all true, then this clause is satisfied if the number of satisfied literals belongs to the set of 1, 2, 3 up to d minus 1. 0 is not good because they would be all false, d would be not good because they would be all true. And I claim that this happens precisely when the following daunting looking expression evaluates to 0. So let's unpack this. All the way at the bottom, we have the value of a literal, which is either just a variable if that literal is positive, or 1 minus the variable if the literal is negative. Then in here, we have the sum over all the literals in the clause of their value. So this sum is just the number of satisfied literals in the clause. And what the total expression now looks like is we're taking the product for I is 1 to d minus 1, and then we're taking the difference between I and however many literals were satisfied. If the number of satisfied literals belongs to this set, then there will be one value of I for which I matches this sum. So then we will get a 0 term in our product and the overall product will come out 0. If the number of satisfied literals does not belong to this set, then this difference will always be non-zero. So then the outcome is a product of non-zero terms. So then the outcome is non-zero. So indeed, this expression characterizes whether or not a not all equal clause is satisfied. And if you look at the degree of the corresponding polynomial you get out of this, then, well, all of the valuations have degree 1 as a polynomial. So we're taking the product of at most d linear terms, or sorry, d minus 1 linear terms. So we're taking a product of d minus 1 values of I. So every not all equal clause can be written as an equality of a degree d minus 1 polynomial. And the fact that the degree is d minus 1 instead of d means that we're saving something non-trivial. If you hammer this through this Gaussian elimination-based framework, turning your polynomials into linearized forms with basically one coefficient for each of the possible monomials, applying Gaussian elimination, then you can find a basis of this set of equalities of size order n to the d minus 1. So it shows that the not all equal set problem has a sparsification down to order n to the d minus 1 constraints, and you can encode it in roughly the same amount of bits. Good. We've taken our first step along the discovery of the island of decision CSPs. If there's any questions, now would be an excellent time. And if not, we're going to explore how we can more formally look at the entire space of all possible constraints and how we can argue about it. Good. Let me introduce you to the concept of constraint languages to formally speak about which types of constraints are possible. A constraint language, gamma, is a finite set of, in our case, Boolean relations. So here is one Boolean relation which contains 3 tuples which correspond to the assignments which are satisfying for this constraint type. And then we can see that a clause on 3 positive variables x, y, and z is 1 in 3 satisfied precisely when the assignment vector of x, y, and z is one that is contained in the set R0. If we include 3 additional relations, then we can also deal with negations. For example, if we look at a clause where the first 2 variables are negated and the last is positive, then this is 1 in 3 satisfied precisely when the assignment to the variables belongs to our relation R2, where we got R2 from R0 by complementing the first 2 columns. All right, I hope you now get the idea, and this leads to the fact that any 1 in 3 clause can be written by saying that the variables involved in it, not literals, but really only variables, are contained in one of these 4 relations, where you pick the ordering of the variables and the relation depending on which variables are negated and which are not. So we can say that 1 in 3 sat is equivalent to a constraint satisfaction problem where the constraints that you're allowed to write come from the set gamma, which has these 4 constraints. So this example leads to the definition of the CSP that corresponds to a constraint language. A constraint language is a finite set of Boolean relations, as we've seen, and for each relation Ri, we denote by arity of Ri the number of variables that this constraint acts on simultaneously. Then the decision problem corresponding to this, denoted CSP of gamma, is the following. As input, we get a set of n variables. We get a set of constraints where each constraint basically tells you, I want to apply a certain relation from my constraint language to variables with these indices. So the second argument is a number of variable indices, exactly arity of your relation many. There might be repeated variables in here, that's allowed. So a constraint tells you apply this constraint, this relation, to this tuple of variables. The question then is, can you find an assignment tau which maps each variable to a 0, 1 value, such that for all the constraints which are on your list, if you plug in the evaluations of the variables, then the resulting vector is an element that belongs to R, to the Boolean relation corresponding to this constraint. So this effectively formalizes the idea we've just seen for 1 in 3 sat. All right, so now we can ask ourselves, how does the choice of gamma affect the complexity of the constraint satisfaction problem? And there's a very nice result, already quite old now, Schaeffer's dichotomy theorem, that says that if you have a finite constraint language built only of Boolean relations, then the corresponding CSP is either polynomial-time solvable or NP-complete. And there's a very elegant characterization of which of the two happens, which is stated in terms of certain closure properties of the relations in gamma and their satisfying assignments. Of course, this is very far from the state of the art in the study of constraint satisfaction problems, where by now the dichotomy conjecture has been proven, where actually also for non-Boolean constraint languages, we know exactly what the characterization is of those which are polynomial-time solvable and those which are hard. However, from a parameterized sparsification perspective, we are very far from understanding anything about CSPs with a non-Boolean domain. So let's stick with the Boolean domain for now and zoom into our parameterized perspective. Given an arbitrary Boolean constraint language gamma, what's the best bound on the sparsification size that we can get? So if n is the number of variables, what's the best guarantee we can give of the form n to the d on the number of constraints or the encoding size after sparsification? So there's been a series of works in this direction, and to give you an overview of what happened, I want to show you a brief timeline. Historically, the lower bounds came first. This paper by Dale and Van Melkebeek, giving the fact that D set has no non-trivial sparsification, its conference version came out with 2010. And in 2015, together with my PhD student Astrid Pieterse, we basically stumbled across an old lemma due to Lovas, and we discovered that using it, we could sparsify the not all equal set problem to a non-trivial number of clauses. We didn't really understand why or how at the time, but it changed 1 year later when we discovered the connection to low-degree polynomials. Then this motivated Victor Lagerquist and Magnus Wahlström to take a universal algebraic approach to constraint satisfaction and sparsification. And they wrote a wonderful paper where they showed how a so-called Maltsev embedding over a finite domain can be used to do reduction also to a linear number of constraints. We don't really have time to go into this technical direction, but I wanted to say that subsequently there was more work based on low-degree polynomial encodings. We managed to find some characterizations pinpointing for certain types of constraint languages exactly what the optimal sparsification is. And last year, together with Michał Wodeszek, we started looking at the maximization version of constraint satisfaction problems. Found an exact characterization of what sparsification is possible there. I'll tell you about it when we hop over to the second continent. And also last year, we proved that at least list H-coloring problems have no non-trivial sparsification. So these form a special class of constraint satisfaction problems where the arity of each relation is 2, but the domain can be larger than 2. All right, that leads me to the Frontiers in Parameterized Complexity workshop here today. So let me tell you what the essential ingredients of this polynomial-based sparsification framework are and how they led to some characterizations of sparsification complexity. Here is the key definition, and since it's quite a mouthful, I'm going to show you the informal statement first. So we say that a Boolean relation of arity k is captured by degree d polynomials. Informally speaking, if you can show that a Boolean assignment satisfies your relation, if and only if it is a root of a set of polynomials that you define. So more formally, your relation is captured by degree d polynomials if you can find a sequence of polynomials. Each polynomial is over the integers mod some integer that you get to choose. Can be a prime, can be a composite. And then you want the following property. If you have a 0-1 assignment, then it satisfies your relation precisely when each polynomial evaluates to 0 with the corresponding modulus. And if your assignment is unsatisfying, then there's at least one of your polynomials on which this assignment evaluates to a non-zero value. All right, this is such an important concept that I took the time to make an extensive example. So let me take you through that. Here is a relation. It's given by the set of satisfying assignments. So this is a relation on 1, 2, 3, 4, 5, 6, 7 variables at the same time. And these combinations are said to be satisfying for this Fano plane relation. There is a more intuitive way to think about what's happening here. This is the Fano plane. Each line is a line, but also this circle is said to be a line. So the Fano plane consists of a bunch of lines, each having 3 points on it, and any 2 lines meet in exactly 1 point. So what are now the satisfying assignments of these relations? These are simply corresponding to every way of setting the variables of one line to true and the rest to 0 is a satisfying assignment and nothing else. So the first satisfying assignment has A, B, and U set to true. So this is A, B, and U. This corresponds to this line. The second is setting A and C and V to true. So A and V and C. This is this line. And all the way at the bottom, we have U, V, and W. That is U, V, and W. It's the line that's a circle. Okay, so now we can forget about this cumbersome table and know that the relation I'm trying to define and for which we will find polynomials that capture what its satisfying assignment are is given by this Fano plane. Now I claim the following. Whenever you have a 0-1 assignment to the 7 variables, then this is a satisfying assignment of our relation if and only if the following things are all true. If you take the values of A, B, and U, then they should sum up to 1 modulo 2. A, B, and U was our first line. If you take the second line, A, M, and W, then the values on that line should sum up to 1 modulo 2. and so on. If you take the last line, u, v, and w, the value should sum up to 1 modulo 2. So I have the constraint that, or in my list of polynomials, for each line, I have a polynomial equality saying that the values along that line should sum up to 1 mod 2. Why is this satisfied for all the satisfying assignments of my relation? Well, if I have a satisfying assignment, it sets some line to true. Clearly, on the equation corresponding to that line, I'm setting 3 things to true, which is odd. If I look at the equation of a different line, then since any different line intersects my chosen line at one point, 1 is also an odd number, so then the corresponding equation is also true. There's a final polynomial equality on my list, and that says that if I sum up all of the values, then I should get to 3 mod 11, but just getting to 3 over the integers would also work. This is demanding that any satisfying assignment must set exactly 3 things to true. And I claim that together, this system of polynomial equalities indeed characterizes what a satisfying assignment is to this relation. To see why, observe that anything that satisfies all these equalities must necessarily set 3 things to true. If the 3 things that you're setting to true do not form a line, so for example, if the 3 things you're setting to true are these, then by the definition of the Fano plane, there is a line through any 2 of them. If this line was not what you set to true, then the third point isn't on this line, but it shows that the corresponding equation for the 3 things on this line is falsified because now we have 2 out of the 3 things on this line set to true, so the sum over this line is even, not odd. So this is a non-trivial example of how a complicated relation with 7 variables can be characterized, captured by degree 1 polynomials in this case. Now, using this notion, we can basically summarize this sparsification framework based on polynomials as follows. If you can capture each relation in your constraint language by a degree D polynomial, then this gives you an algorithm to reduce an n variable instance of CSP gamma into an equivalent instance, one with exactly the same satisfying set of assignments, not just the same yes-no satisfiability answer, such that the number of constraints is on the order of number of variables to the d, where this d is a degree of the polynomials you needed to capture these relations. This reduction algorithm is essentially doing Gaussian elimination, and the big O here hides factors which depend only on gamma. Good. If you have any questions so far, now would be a good time. So this polynomial framework summarized says that if each Boolean relation can be captured by degree D polynomials, then you can sparsify CSP of gamma to order n to the D constraint. This is a pretty powerful tool, and it raises us several questions. First of all, you can ask yourself, for which type of relations can I capture them using a polynomial whose degree is strictly less than the arity of the relation? It is trivial to capture a relation using the degree equal to the arity, and you get a better than worst case or non-trivial sparsification whenever you can shave at least 1 off the degree compared to the arity. So the first question is basically, for which types of relations can I have a non-trivial sparsification? Recall that, for example, for 3CNF-SAT, there was no non-trivial sparsification possible. Removing duplicates was the best we could do. A second type of question looks at the other end of the sparsifiability spectrum and asks for which types of relations can we have the best possible sparsification behavior. And this corresponds to relations you can capture with a degree 1 polynomial, because then you get a linear sparsification out of it, which is the best case possible. So over the last years, we've actually managed to answer both questions, and there are elegant characterizations of the answers. So let me try to tell you. We are going to start by looking at when is non-trivial sparsification possible, corresponding to relations that can be captured using polynomials whose degree is strictly less than the arity of the relation. So let K be the maximum arity of a relation in our chosen constraint language. If we consider gamma to be a constant, then there are order of n to the k possible constraints that we could write. Right? There's size of gamma different constraints to apply. For each constraint of arity at most k, there's n to the k different ways to choose the indices of the variables on which these are applied. So when can we get something non-trivial? When can we get a sparsification where the number of constraints we left with is something bounded by n to the k minus epsilon for some positive epsilon? The answer turns out to be when each arity k relation in your constraint language has a number of falsifying assignments other than 1. So let's read through the statement. Recall that k was the maximum arity of a relation. If each maximum arity relation has the size of the set of assignments which are not satisfying assignments unequal to 1, so number of falsifying assignments is unequal to 1, then we can efficiently sparsify CFP of gamma to order of n to the k minus 1 constraints. So then we can save at least 1 in the exponent corresponding to the trivial sparsification that just eliminates duplicates. And the reason is that if the number of falsifying assignments is not equal to 1, then you can use this fact to write down a polynomial that captures this relation and the degree is at most k minus 1. So this gives an upper bound for a lot of constraint languages, and we have a matching lower bound. We also proved that if your constraint language has an arity k relation for which the number of falsifying assignments is exactly 1, then this CSP has no efficient sparsification to order of n to the k minus epsilon constraints for any positive epsilon. Again, assuming that NP is not in co-NP poly. So this is very closely related to the fact that the CNF set problem has a Boolean OR as its type of constraint, and a Boolean OR has only one falsifying assignment, namely setting everything to false. So here we see that while historically speaking, the fact that CNF set has no non-trivial sparsification was the first we knew, and only later we found that in some cases there is a non-trivial sparsification to be found, we now see that CNF set is pretty much the only problem for which there's no non-trivial sparsification. Because whenever you have a Boolean relation with exactly one falsifying assignment, then up to negations, it basically acts as a Boolean OR. Let me point to the first of some open problems that I've sprinkled throughout the talk. It's open whether you can do non-trivial sparsification for larger domains under such a general condition as the one we've shown. So we've pinpointed which Boolean gamma allow for a non-trivial sparsification. For constraint language over larger domains, we don't know. So as a very concrete open problem, characterize those finite constraint languages gamma on a domain of size, say, 3, for which the corresponding CSP has a non-trivial sparsification. So a compression to n to the k minus 1 bits of the polylogs, where k was the maximum arity of your relation and constraint language gamma. All right, let's take a breath. We have already covered some ground. We have made it through the notions of non-trivial sparsification, and we continue climbing towards greater generality. When you can capture your relation by a linear degree 1 polynomial, then we got linear compressions. So those were very good. And let's see when that's possible. We need some closure property on the set of satisfying assignments. So we say that a Boolean relation is preserved by all alternating operations if for all sequences of satisfying assignments to this relation, the following holds. If you add component-wise and subtract the satisfying assignments like this, and the outcome of that is a 0-1 assignment, then this has to be a satisfying assignment. So a relation is preserved by all alternating operations if whenever you take an alternating sum of satisfying assignments starting and ending with a plus term, and the outcome is a 0, 1 assignment, it should be a satisfying one. So as a non-example, let me show you that Boolean OR is an operation that's not preserved by all alternating operations, because if we take the 3 satisfying assignments 1, 0, 1, 1, and 0, 1, and we alternately add and subtract them, then we get a Boolean assignment 0, 0, but this is not a satisfying one. So this shows that the Boolean OR is not preserved by alternating operations. But for example, the 1 in 3 constraint is preserved. If you would try the same trick here, you take 1 satisfying assignment, subtract the second, add the third, the outcome is not a 0, 1 assignment because it has a -1 here, so that's fine. That's not something that the condition prevents. And using this terminology, we could characterize which Boolean relations you can capture by a degree 1 linear polynomial. Precisely those Boolean relations which are preserved by all of the alternating operations of this form. So from a mathematical perspective, this shows you when a linear representation of a constraint is possible. And from a sparsification perspective, we can now use this to make some characterizations. We say a relation that's preserved by all alternating operations is balanced, and a constraint language consisting only of balanced relations, we call it in total balanced. What we've seen so far implies that if your gamma is balanced, then CSP gamma can be sparsified to a linear number of constraints. I see that there's a question from Eindhoven Kim. What is n here? N here is any integer. Sorry, it's not related to the number of variables because this works on the level of a constraint language, so there's no particular input yet. This just says for any odd length sequence of alternating between adding and subtracting a satisfying assignment, if this arbitrary length sequence of adding and subtracting comes out to a 0, 1 assignment, then it has to be a satisfying assignment. Thanks for the question. So as a consequence, we get that if your constraint language consists only of these balanced relations, you can do a linear sparsification. And if it's not balanced, then there is some witness that it's not balanced in terms of this alternating operation that combines satisfying assignments into an unsatisfying one. And this witness can sometimes be used to make a lower bound proof for sparsification. And we'll see an example of a type of lower boundary proof for that in a minute. Before we do, let me point you to this open problem. And that is if you can do something beyond linear combinations. We've been working on this general principle that if each constraint is equivalent to an equality, and the equality for constraint C is a linear combination of other equalities, then it's redundant. So this polynomial-based framework detects redundancy basically by expressing it as a linear combination of others, but it would be very interesting to see whether some nonlinear proof system, such as sum of squares, could efficiently detect redundancy of some constraint types not covered by a framework. I've tried to think about it on a couple of occasions, but as I'm not an expert in sum of squares, I haven't reported any progress yet. All right, we made our way past the balanced relations, and we keep climbing our way up to the generality of CSP gamma. So the one setting in which we can make a characterization of when linear sparsification is possible is for symmetric CSPs. We call a relation symmetric if the satisfaction of the constraints just depends on the number of true values and not on where they are. So a symmetric relation is characterized by the weights of the satisfying assignments alone. If you have a constraint language built only out of these symmetric constraints, then we say it's symmetric. And if you have such a symmetric intractable constraint language, so the problem CSP gamma is NP hard, then we have the following characterization. You can efficiently sparsify it to a linear number of constraints if and only if this constraint language is balanced. So in this sense, the property of being balanced and this polynomial framework correctly pinpoints all the cases that have a linear sparsification. If you fail to be a balanced constraint language, then we can prove a quadratic lower bound for the corresponding sparsification question. So in this sense, the property of being balanced turned out to be the right one, at least for seeing what happens to symmetric CSPs. What happened beyond symmetric constraint language is wide open though. So for non-symmetric constraint languages, the property of being balanced is sufficient to ensure we get a linear sparsification, but we don't know it to be necessary. So a very interesting, if you ask me, open problem is to characterize for which non-symmetric Boolean constraint languages CSP of gamma admits a sparsification to a linear number of constraints. All right, we're almost to the top, and the top has one more characterization that I want to show you. And this characterization basically says that we know what the optimal sparsification size is for a number of constraint languages built out of small arity relations. It's in terms of something we call cone definition. And without showing you the formal definition, let me just show you that some relation like 3 not all equal can implement the Boolean or, because if you want to know whether an XY setting satisfies Boolean or, then you can plug in X and Y and the constant 0 and check if the resulting tuple satisfies 3 not all equal. So in this way, you can make a general framework for defining one relation by plugging it into another with negations, repetitions, and constants, but without introducing fresh variables. This is not a positive primitive definition or such a thing. So using this notion of can you define one relation from another by plugging in constants and negations, we can give the following. If we have a constraint language consisting only of relations of arity at most 3, so this is a restricted setting we can look at, then at least it's true that if you look at the largest Boolean or that you can define just by plugging it into one relation, then this is what characterizes the sparsification behavior. CSP of gamma has a sparsification with order of n to the k constraints, but no sparsification with order n to the k minus epsilon constraints for any positive epsilon. So at least in the regime of relations of arity at most 3, there is an easy answer to what the optimal sparsification size is. And it shows that also here, this polynomial-based framework gives us the optimal sparsification size. It is known, however, also thanks to the work of Lagerquist and Wallström, that this type of characterization is not true indefinitely. It fails somewhere in the range of relations of arity 20. Maybe for 4 and 5, this is still true. All right, we've made it to the top of the mountain of the decision CSP island. We can enjoy the view, and since we've been having very nice skating weather in the Netherlands, I thought I'll give you a sample of the view of the Netherlands, which is not really mountainous, but at least this is what the Netherlands looked like a week and a half ago. This is a canal just outside my town, and we went for a skate out here. While we are enjoying the Dutch scenery, I wanted to add the following. It's not often that we have tulips at home, but to complete the picture of a Dutch scenery, this is, I think, as Dutch as it gets for the moment. Having honored the Dutch flag in this way, it's time to hop over to the island of maximization CSPs and see what things behave like down there. So in decision CSP, we ask, can all constraints be satisfied simultaneously? In max CSP, the question is, even if you can't satisfy all of them simultaneously, what's the maximum you can simultaneously satisfy? And for a certain fixed gamma, decision may be easy while maximization is hard. The school example is that 2SAT is polynomial-time solvable, but max 2SAT is NP complete. So then the question that we started asking ourselves is, can we apply sparsification also for max CSP problems? When we're in this regime, it turns out to matter how often the same constraint occurs, right? Because you score for each time that constraint occurs and is satisfied. We model this by saying that each constraint has an integer weight, can be positive or negative, but its absolute value is bounded by a polynomial in the number of variables. And then max CSP has a decision problem, which is what we study algorithmically, and the decision problem asks, is there an assignment for which the number of satisfied constraints and their total weight sums up to at least t? Let's think about whether the approach that we started for decision CSPs is any good here. The principle that we used for sparsification of decision CSPs was this redundancy. If you can show that a constraint is a linear combination of others, then it must be satisfied when the others are satisfied, and you can forget about it. This completely breaks in the maximization setting, right? If you are a linear combination of some constraints which are not all satisfied, then you have no guarantee of whether its linear combination is satisfied or not. So redundancy-based sparsification seems to be out of the question. And also the fact that if you forget about a constraint, you don't know if you score it or not, seems to be a big issue. There is a different approach, though, to compressing inputs of max CSP problems. It's again based on some polynomials, but different types of polynomials than before. It's related to characteristic polynomials, which have popped up in complexity theory over the years more often. For a Boolean relation, its characteristic polynomial is the unique k-variate and multilinear polynomial over the real numbers, which basically gives 0 for all the unsatisfying assignments and 1 for all the satisfying assignments of your constraint. So for example, for the 1 in 3 constraint, the characteristic polynomial is as follows. If we plug in a satisfying assignment such as 0, 1, 0, then this polynomial evaluates to, well, we get a 1 here, we get all zeros in these products, and this is a 0. So if we put in this satisfying assignment, we get out a 1. If you put in the unsatisfying assignment 1, 1, 1, then you score 1, 1, 1 here, you score 2, 2, and 2 here, and you score 3 here, and in total, this sums to exactly 0. Let's do a second example. For the not all equal SAT problem, where a constraint is satisfied if the values are not all equal, the polynomial is of degree 2. And let's see why. If you put in all zeros, then the polynomial comes out 0. If you put in all ones, then you score these values all evaluate to 1. These pairwise products all evaluate to 1. So we have 3 minus 3 is 0. If you plug in anything else, you'll get out a 1 value. If you have 1 true and 2 false values, you'll score a +1 and you don't subtract any of these pairwise products. If you set 2 things to true and you score twice an individual +1, you subtract a single product of 1, so out still comes the value 1. So note that this is a more demanding definition of our polynomial as before, because we demand now the same output value for all satisfying assignments, but we also demand the same output value for all unsatisfying assignments. Also, we're not allowed to use any ring other than that of the real numbers. All right, let's see what these characteristic polynomials allow us to do in the land of max CSPs. And already quite directly, we can get some compression algorithm out of it. So observe the following. If we have some weighted constraint, which says that you apply this relation to this sequence of variables and you score this weight if the assignment is satisfying, then what's the contribution to the total score you get for this assignment? Well, this contribution is exactly W times the value of the characteristic polynomial on the corresponding variables, because this polynomial gives out 0 and 1 exactly based on whether this assignment is satisfying or not. This means that if you have an instance of max CSP with some weighted constraint, then the total weight of the constraints which are satisfied can just be written as a sum over all the constraints you have of the score you gain for this constraint, if it's good, multiplied by the corresponding polynomial applied to the variables it deals with. This basically says that optimizing the weight of satisfying constraint is equivalent to finding a 0-1 assignment that maximizes this weighted sum. But now let's see what would happen if we take this weighted sum and we group terms for identical monomials and just add up all their coefficients. If we would expand all of these terms and then collect them, if the maximum degree of the characteristic polynomials is d, then each of these individual applications has order n to the d distinct monomials. And if you collect terms, you only have to store order n to the d coefficients to tell you what the exact weighted sum looked like. Recall also that we assumed that the absolute value of each weight is bounded by a polynomial, and that the total number of different constraint applications, since we demand that each tuple of variables can be applied for one relation at most once, After collecting terms, this means that each coefficient has bit size order log n, because a polynomial in n quantity you can encode in order log n bits. So this gives us a monomial-based compression for the problem that says if the maximum degree of all the characteristic polynomials is d, then you can compress an instance of max CSP for this gamma into a different type of representation, a representation in terms of does this weighted sum have a 0,1 setting that makes it come out at least at its threshold, but at least the encoding size of this new representation of the problem is bounded in order to the n to the d times log n bits. So this is not really sparsification. We're not finding a subset of the constraints that preserves the answer, but at least we're finding a small representation that gives you the same answer. Later in the talk, towards the end, we'll see how we can get an actual instance of the max CSP problem that has the same answer. First, though, we'll look at the size guarantee. How good is the compression we get in this way? And it turns out that these characteristic polynomials compress optimally. Given a constraint language, let's define its degree as the maximum of the degrees of the corresponding characteristic polynomials. We've just seen that we can compress an instance to one of bit size order n to the degree of gamma times log n. And this turns out to be optimal for all of the NP-hard Boolean max CSPs. If your max CSP is NP-hard, then it doesn't admit a polynomial time compression whose bit size is n to the degree of gamma minus some positive epsilon. So already this sort of simple sparsification scheme, at least in terms of number of bits of the compression, gives you the optimal answer for all NP-hard Boolean max CSPs. And the fact that this fairly straightforward approach gives you an optimal answer for max CSPs, whereas we had a very intricate analysis to capture only parts of the decision CSPs, comes intuitively from the fact that there are more NP-hard cases for max CSP, which means that we need only to show that the lower bound holds and there's less of the positive cases with intricate behavior that we have to deal with. So our main work is improving this lower bound. Before I show you some of the ideas in the lower bound, I just wanted to show you an overview of what does this mean for the complexity of sparsification when we compare decision versus maximization CSPs. So what we can do is compute the degree of the characteristic polynomials for various classic constraint types and then see what comes out. And we see something very strange. In this column, we have optimal compression sizes for decision CSP. In this column, we have optimal compression sizes for max CSP. If we look at not all equal set for odd d, then we get n to the d minus 1 compression size. If we look at not all equal set for even d, we will get n to the d compression size. So here, we don't always save one in the exponent, but we only save one in the exponent when d is odd. And this turns out to be related to the fact that this characteristic polynomial turns out to have degree d when d is even and d minus 1 otherwise, due to some cancellation property of binomial coefficients. For other problems, for example, for 1 in dsat, we had this near linear compression for the decision problem, but we cannot do anything non-trivial for the maximization variant. So intuitively, the stronger restrictions on the polynomials that we have to employ for max CSP mean that we cannot get the same savings as for decision CSP, but by our lower bound, this is unavoidable. Speaking of the lower bound, let me try to illustrate it, and at least one example case which should be striking. That this 1 in 3 set problem, which in the decision version has a linear sparsification, in the maximization version it doesn't have any sparsification to less than a cubic number of bits, so nothing non-trivial can be done there. To simplify this proof, I will allow myself to use the constant false in an input. Let me just say that you can avoid it with some more work. The proof strategy is as follows. To give a linear parameter transformation, which starts from 3 CNF-sat, for which this cubic lower bound was known, and then transform an input with n variables into an n variable input of max 1 in 3 sat. The main ingredient is the following. There exists a collection of weighted constraints, I'll show you the collection in a minute, on 3 variables and the constant false, such that if the Boolean OR of these variables holds, then among this collection, the weight of the satisfied constraints is 1. If the Boolean or of these variables is false, then among this collection, the satisfied weight is exactly 0. So that by plugging in this collection, we can basically test if the constraint is satisfied because we'll score 1 or 0 for it. This is what the collection looks like. We apply the 1 in 3 constraint to our 3 variables, and if that 1 in 3 constraint is satisfied, we score plus a third. We apply also to x1, x2, and the always false constant. If it's satisfied, we score 1/6, and so on until here we apply it to x3, false and false, and if it's satisfied, we score a third. Let's see why this does what we want. If you have the all 0 assignment, which is an unsatisfying assignment of the Boolean or, then the satisfied weight of this collection should come out 0. Well, that should be easy to see because our 1 in 3 constraints demand that one thing in their input is set to true. We're always feeding at least one of our input variables in there. So if they are all false, then we will always be evaluating 1 in 3 false, and we get out 0, we don't score the constraint. Now suppose that we have a setting which satisfies this Boolean or because it sets x1 to true. Then in this 1 in 3 constraint, x1 will be true, 2 and 3 are false, so we score it for a weight of 1/3. In this application, x1 was true, but 2 is false, and always false is also false. We score this one. For the same reason, we score this one, but the x2, x3 are false, we don't score. And similarly, these two we don't score, and this sums up to 1. Let's look at one more case in the table. If you set all variables to be true, you don't score any of the first ones because there will be at least 2 trues among these, but you will score the last 3 because x1 will be true as the only one here, x2 and x3, so you score 3 times a 1/3, a 1. So this is the main ingredient for this lower bound proof. Because once you have this, if you want to reduce a 3 CNF set instance f to a max 1 in 3 set instance, you simply do the following. For each 3 clause that you have, you insert the weighted 1 in 3 constraint on the corresponding literals. That's it. The number of variables n doesn't change. And then we know that since this collection will always score us either 0 or 1, and it only scores us a 1 if the clause is satisfied, we find that the formula f is satisfiable if and only if there is some assignment to the max 1 in 3 set problem that scores a total weight of m. So this gives that the max 1 in 3 set problem does not admit a polynomial time compression to a subcubic number of bits, again, unless NP is in co-NP poly. For the general lower bound, where I claimed that the sparsification obtained by this characteristic polynomial compression is optimal, we have a similar scheme. So it basically says that if there is a Boolean relation in your constraint language whose characteristic polynomial has degree d, then it's possible to construct a collection of weighted constraints over R, over your variables and the constants, such that if the Boolean or of d variables is satisfied, then this collection scores 1. If the Boolean or is not satisfied, this collection scores 0. And we can construct this collection recursively by analyzing terms of the characteristic polynomial. And that's where the interaction between the characteristic polynomial's definition and this lower bound construction comes in. Using this collection, we can make a reduction from D CNF set to our problem that doesn't blow up the number of variables. We can gadgeteer out the constant true and false using known ideas, which were also used in inapproximability results for CSP based by Cannon, Sudan, Trevisan, and Williamson. And we can also do some gadgeteering to get rid of the negative literals so that we can be in the pure CSP framework. And this proves our main lower bound, that if max CSP is NP hard, it doesn't admit a polynomial time compression, better than the one that we gave. We're almost through. Let me just flash you the island of kernelization, which says that rather than just compressing to a monomial-based representation of the problem, we could also compress to the same problem. We don't know how to sparsify to a subset of the constraints that yields the same set of optimally weighted assignments, but using similar techniques as in the lower bound, rewriting one constraint in terms of others, we can do a self-reduction. And the final theorem we proved is that max CSP gamma with polynomially bounded weights can be reduced in polynomial time to another instance of max CSP gamma, still only on order of n variables. The number of constraints is on the order of n to the degree of gamma, and the weights is still polynomial in n. So this is the self-reduction, almost a kernelization that we have. That brings us to our final stop, also in the continent of max CSPs. So all that's left for me to do is to conclude. We've seen that algebraic sparsification of CSPs can yield several optimal sparsification results. For Boolean CSPs, by now we know explicit characterizations of which of them admit a non-trivial sparsification, which symmetric problems admit a linear sparsification, and for all max CSP gamma problems, what the optimal compression size is. Let me reiterate some of the open problems. One would be to fully characterize all of the Boolean CSPs, even the non-symmetric ones that have a linear sparsification. Also analyze sparsification complexity for non-Boolean CSPs and non-Boolean max CSPs. I want to briefly shout out that I have a postdoc position available. If you know anyone who's interested, the call was on DMAnet a minute ago. And with that, I want to thank you for the attention, and I'll be happy to take any questions you may have.
Thank you very much, Bart. You know, you have to pay for their announced positions for commercials. Yes, please, questions, please.